So if you have something, please send it. Okay, so today we have a short day, just the morning, and then the afternoon is off, as we mentioned yesterday. And those who don't want to go sightseeing and hang around here, we can do discussion. We'll do it as we'll see how it goes. Okay, so the first speaker today is Morten Andersen and Jordan Snyder, and they're both from Roskilde University in Denmark, and they work on blood cancers, and we talk about mathematical models of blood cancer and premalignancy.
Thanks a lot. Yeah, we will join this the stage together, but there will be something old and something new, and I'm the old, and this is a new. So if you want to sit down first, then Jordan will tell you about some of the new stuff later on, and I'll tell you about some of the old stuff. Speaking of artistic contribution, I want to acknowledge Thomas Steele for this very nice artistic contribution. I modified it a little bit, but it's beautiful. What we do, and what I've been a part of for 10 years, is what many of you guys are also doing, but we try to put it into a nice figure, to really, together with clinicians, take their biological knowledge and from that transform into mathematical models, like many of you people do. Then by use of mathematical analysis and computer simulations and hopefully clinical data, we can get some understanding of the biological processes that are going on, and use that to better understand disease and to help predict disease outcome, maybe optimize therapy, maybe come with some new suggestions. So what many of you guys are doing in one figure. Right. So again, what many of us are doing, we have been doing for quite a while, or other people before us have been doing for quite a while. So I like this review by Helen Byrne showing the timeline of the history of mathematical modeling of cancer, going quite far back, and with contributions from people in the audience here. And again, what I think joins us all together is this idea that mathematical models represent a framework for testing biological hypotheses and generating new ones, and to use that maybe also to optimize some experimental protocols. Okay, so this was like the broad intro. So who are we? So these are my closest colleagues. So from math, we have my close collaborator, Johnny Andersen, and PhD student Tobias, who's been doing some of the work. Johan is mathematician. Oh, Thomas is here. So Thomas got a grant to be a part of the group here, and to work with and to hire Jordan and Johan and so on, looking into some of the stuff Jordan will tell you about later. Then we have the clinicians. So Hans Hasselbach is a clinical professor, like the grand old man of blood cancer in Denmark. And he's located at the neighboring hospital. And he's brought biologists with him, molecular biologist Wiebe, and Lasse is not here, and medical doctor Trine here. So we're like a broad group that meets once a month. Then of course we have the more local mathematics at the university. So what is the goal here? So it's really Hans who came to us almost 10 years ago now, asking about whether mathematics and mathematical modeling could help address these questions, which I think is quite a strong thing to do, because Hans knows nothing about mathematics or mathematical modeling. But what Hans is interested in is to study the specific blood cancers that we heard Kit talk about yesterday, the MPNs, myeloproliferative neoplasms. I spelled it wrong and I said it wrong, but we just called them MPNs. So these are slowly developing blood cancers. In particular, Hans was interested in the relation with chronic inflammation, because he and others has the perception that chronic inflammation is kind of going into this bad cycle where it upregulates the blood cancer, and the blood cancer upregulates the chronic inflammation, and then we have this bad circle going on. So since it's a slowly developing blood cancer, and not many die from it, and it's quite rare, there are different strategies. There's like a watch and wait, and there's let's do something about it. So let's see if mathematical modeling can also help in that aspect. Then there's what kind of treatment should you actually use. So Tobias is working on different combination therapies. And then there's the problem of all the undiagnosed cases. So even though it's rare, we heard yesterday that the majority of MPN patients has this JAK2 mutation. So that is a rare mutation. In the background population, it has now been found that it's actually 10 times more prevalent than what people used to think, because they now got better assays, which are 10 times more sensitive. So the background prevalence is 3%. That is a paper by Cordo et al. From Blood 2019. So that is a rather large number, 10 times larger than what was expected. If we go to the stroke unit and ask them how many of the guys who get a stroke actually had the JAK2 mutation, they didn't know 1 year ago. But now they found out that the prevalence of the JAK2 mutation for stroke is 11%. So one of the big problems here is really all the undiagnosed cases of MPNs, where people walk around, get a stroke, and maybe they don't even figure out that it was in an undiagnosed MPN at that time.
So the 3% prevalence, is that among everybody?
Yeah. So that is a general population study.
Okay, so not age.
But you can see the age. Of course, it changes with age, and you can see that. So I can give you the reference. Cordua et al. 19. I believe it's Blood. Otherwise, I'll find it for you. I am actually not sure whether this is only in review or published yet, because we just had it at a recent seminar. Okay, so that is an important reason to study these cases and to look into also whether mathematical modeling can say something about what are the windows of opportunity to do something here. Then what Jordan will come and talk about is this pre-disease state. So you can have this JAK2 mutation, but not having any kind of diagnostic criteria otherwise fulfilled for being sick, but you will have a high risk of developing the disease. So what's the dynamics here? What can we do here as mathematical models? And then also, as I said, with this chronic inflammation, the immune response is an important factor, and we should look into this. Okay, so we heard a little bit yesterday. So blood is formed in the bone marrow. We have this hierarchy with stem cells at the top that differentiate into both different lineages and more specialized cells here. What might happen is we get a malignant mutation, which is worse if it happens at this end of the tree, where the JAK2 mutation can happen. So that's the general picture. And this is a good time, I think, to stop and pause to think, how much blood do you have? How long is the blood in you at a time? What's the lifetime of the blood cells? So if you sit completely still, right? Try to do nothing. In this span, you made millions of blood cells. So on a daily basis, you make 100 billion blood cells. So if you're a physicist, the number of stars in the Milky Way is equal to the number of blood cells that you produce daily. So a huge number. And how big is that compared to other kinds of cells, cell turnover in the body? Well, there was this really nice paper by Snyder and Milo a couple of years ago that gathered information about all kinds of cell turnover in the human body. So you see here 10 to the 11th cells per day. Everything that's color-coded red has to do with blood cells. So really, the majority of cell turnover in the human body is blood cells, and 100 billion cells per day. So
what's the
there's no excesses here.
Oh, it's just a diagram.
Yeah, it's just yeah. So it's just showing you how much of this. So since we cannot live with, making 10% extra or 2% extra or a small percent extra blood every day, if it's accumulating, there must be feedback signals in your body that is really regulating this. And this also tells you, just a small problem here can cause a long-term problem. And this is the kind of problem we have with these MPNs, that you get too many blood cells over time. Right, so then to some mathematical modeling, we group some different cell pools together to make an ODE model. So we have the stem cells and the early progenitors, and we only look at mature cells where we can have measurements from the peripheral blood. And we have a similar structure for the malignant parts, so the JAK2 mutated cell line. And then we want to include also this inflammation. So there is, as I said, some evidence that inflammation has a feedback to the stem cell pool. And we include this in this diagram here. So it might look busy if you forget about this side first and just think about this as being 0. This should be a model of hematopoiesis. So we have the hematopoietic stem cells. They can self-renew, they can die, they can differentiate in a number of steps. So this is this multiplication factor. We could have included more compartments here if that was useful. There needs to be at least 17 if you know the number here and the number here, and one cell can become 2. Then the mature blood cells do their job and they die at some time, and then the immune system, which here is just one compartment, very simplified, is taking care of the dead cells and then can upregulate the hematopoietic stem cells. Then what can happen is that we can have a mutation here from the hematopoietic stem cells and get these JAK2 mutated ones. And oh yeah, and I forgot, so there is also this negative feedback here, which could be, of course, the mathematical form could be interpreted in many ways, making sure that if you have too little or too few, you can go back to steady state. So this is kind of what assures that you will have hematopoiesis without this part. So for example, if you donate blood, there should be a mechanism that it's restored, and you have some typical times for how fast that happens, and you can use that to estimate some of the parameters here. Yeah. I didn't get that.
So you have an arrow.
Yeah.
You have arrow in and arrow out each compartment.
Mm-hmm. Let's see when we have the equation. It's a matter of it's a second order effect. So that is just why it's put like that. But we could talk many ways that this could be implemented in equations. This is one choice, yeah?
Sorry, the question, sorry to interrupt. So inflammation is caused by a certain type of blood cells, right? So in some sense, if you have more blood cells, you would think that could lead to also more inflammation.
Yes. Yeah, exactly. And this is, you also have that here, yeah.
Oh, okay, because there's no arrow there from such a death of inflammation.
But it's kind of acting through.
Well, I didn't mean through necrosis.
Yeah, no.
Yeah. Just the fact that you have more white blood cells.
Yeah, I will not claim that this is the only model that has the relevant biology, and I would love to discuss. I mean, I should have said many other people have looked at models of similar things, Thomas, Dominic, and so on. So this is one, and it's also our first one. So I said something old, right?
So does it have to be dead cells that cause the inflammation, or going to be live cells as well? Because some mutant cells, right, specifically increase inflammation, and then the inflammation seems to affect the self-renewal probability.
Yeah, so that could be done in a different way also, I guess. Yeah. But this negative feedback here, once we have the mutated cells arriving, is coupled, right? So that's why we have this. You'll see in the equations in a second. So they can be more or less sensitive to the presence of the other one. So you kind of have that idea that the inflammation can be more favorable to the mutated ones and provide this a better environment for them to grow in. So we looked at different ways of formulating this into differential equations, and this was our first take. So self-renewal, this negative feedback, which can be formulated in many ways and give similar results. Death terms, amplification factors, the mutations. Here just really an amplifications in the mature blood cells. Yeah, and then a similar situations for the other one. And we had this these C's here to accommodate for different weight on the self-renewal for the different cell types here and here. Okay, so we talked about complicated models and less complicated models. The medical doctors find this to be very complicated. I think that on the axis we heard about yesterday, from Eduardo to David, we're still close to Eduardo with this one with 6 coupled nonlinear differential equations. Right. So we got from the literature some. So one of the things that why is it? No, it's wrong. Like one of the things that we want to improve on is this information compartment here. But what could it mean? So there are different markers for inflammation that different people think are the most important, and some of the inflammatory cytokines we have here from the literature doing MPN progression, and you could fit the model as such and take one of these to be your favorite inflammation marker, and there's at least growth in them, and you can see growth in the model. There's one maybe not, but there's some relation to that. Then if we use the model and take the biological information available, the number of stem cells, the number of peripheral blood cells, and the death rates, and what we can find, and we come with one JAK2 mutated cell, and use this idea that it is slowly developing disease. So time 0 here is really the time of the mutation, not the age of the person. And of course, that could be adjusted. You can adjust that time scale as you like. We see here to the left, the stem cells and the blood cells looking very similar, different scales. After, I don't know, 40-something years, that could be kind of a marker of that the disease has reached a little burden, 50%. What happens if you increase, let's go back, this inflammation here by some factor, for example, due to smoking? You get this, and you do that before you feel sick. You get this speeded up development. The 2 curves cross at a much earlier time. So that is some mathematical, I don't know if call it evidence, that chronic inflammation can kind of speed up this process if that is. So here it's yeah. So it can be implemented in many different ways actually, but for this simulation it was that the RY was bigger than the RX, so the self-renewal was. How much did you? I cannot remember. I can find it, but you can actually you can make it in many ways, because you can also do it by assuming different numbers here. So this was one way to do it.
Because the magnitude of this will.
Yeah. Yeah, so we assumed similar parameters for the healthy and the malignant part, except I think the R's in that simulation here, to kind of not have too many degrees of freedom at this point. So yeah.
But I'm a little confused. Were parameters fit the data, or are they just taken out of the?
So there will be something with clinical data later on. The parameters were chosen from the known biology, like the number of stem cells, the self-renewal, stem cells self-renew once or twice per year, the lifetime of the healthy ones. If you take some blood out when you're in a healthy condition, does it kind of bounce back fast enough? So it was not, I would not claim that it's not over parameterized, but it's done at least with some thought behind it. The what? Yes, but it has it. So yes, it does. But the feedback here could be implemented different, right? Okay, so this was still at the stage of kind of generating ideas. So I guess that what you observe here is also that this picture looks very much like this picture. This picture looks very much like this picture, and that is supported by different time scales here. So really, the stem cell dynamics is fast and the rest of the dynamics is slow. So that suggests a positive state approximation, where you basically set this guy, this guy, this guy, and this guy to 0 as a reduced model. So you have a 2-dimensional model. Sorry, opposite. Thank you. That is slow on the other one. I'm very happy you said that. It was the other way around. Yeah. Sorry. So this was a full model, and now we are here with Eduardo on a 2-dimensional nonlinear model, right? If we do that, which means we can do more analysis. And I think one nice thing about starting big and then going smaller is that it means that some of the parameters in the lower dimensional system then is a group of parameters from the big system. So you still have some information about if I go and change something in the 6-dimensional model, how would it influence? And this, we have played around with that kind of idea. So if you do that and have this 2-dimensional model, you could look at what happens if we have untreated growth. So this is the curve we have here. And then we look at patients with MPN, but treated with a specific drug, namely interferon alpha, which I hope it says here somewhere. Yeah, here, which is known to have an effect at the stem cell level. So therefore, it should have an effect on this quantity here. So these are stem cell parameters. And in the reduced model, this lumped parameter is kind of coming out of the analysis. And you can do global analysis here in this case and actually show that depending on whether this guy is bigger than or smaller than 1, you would have that the allele burden will grow or it will decay, just like we have all learned with the SIR model during the pandemic. So it's kind of a similar feature. So here we can fit just one parameter, this guy here in the reduced model, and get this kind of curve from the literature. So just fitting one parameter, which we liked. Okay, so let's go to kind of our own data. This was data from the literature. So our clinical collaborators have set up a few years ago this big trial, considering how few have the MPN, where 200 patients either were given this interferon in 2 different forms, or hydroxyurea, which is not expected to work at the stem cell level, but is cheap and is used many places, and which prevents new stroke mostly, or helps with that. So we talked about what kind of data to get, of course, and this is basically, so this is all of Denmark. Welcome to Denmark. There's a 5-hour drive from where we live to this place here. So this is how small it is. And these are the different sites. So it's really a national study with this MPN here. So of course, some patients respond well, some don't respond so well. Those who respond well, if we kind of look at the response curves here, there's some kind of exponential trend. And Mark, one of our PhD students, have looked into modeling this with a hierarchical model and found that you have a half-life typically around 1.2 years when the drug is doing its job. Okay, so this is kind of like a data analysis fitting. What about our mechanism-based model? Yeah.
Are you fitting each patient separately or the mean of the patients? Because you could argue different patients have different parameters.
Yeah, but so this is why it's a hierarchical model. So you have you think. Oh, let me see if I can remember it. Well, let me look that up, not to say something, and then we can talk about it later. I can recall. Right. So what about taking that kind of data and looking at the well-behaved patients in the model? So one thing that the model can do that the clinicians like is, of course, to couple the hematological quantities, which is the typical things they measure, like leukocytes and thrombocytes, and then what they call the molecular quantities, this JAK2 allele burden, which is measured for this trial, but which is not done routinely across the world. And here we have many serial measurements, and we have the drug dose. And we then also implemented like a drug uptake model here. So with this idea before, with this threshold value, we can, for the specific patient, say something about, I mean, if you believe in the model, of course, a threshold for how much interferon do you need to give to the patient to actually go from an increasing allele burden to a decreasing one. So this is the color coding here with the red and blue throughout the next pictures.
Is it the blood?
Yeah, so it's from the peripheral blood, yeah. So we could do that for different patients coming in with different allele burdens. So the clinicians would all put this at time 0, since we think of the disease as growing, you know, from the same kind of growth initially. Of course, it can be different, but it has to start and then grow. We put it on this, our master growth curve here, and then said, okay, so one patient started here, one came in a bit later. And then for each patient, we adjusted just this one parameter that I talked about before. And I think we could get some nice fits for that, which is again coupled to this biological understanding of what the drug is doing. So the master curve is not using, you could say we put the first data point at the corresponding allele burden at the master curve, right? So we have this as some growth. Yeah, so there are different things to reply here. So of course, this guy here and this guy here will not have followed the exact same path, but we don't have that data. Right. Jordan will talk about that because now we may have the data, but at this point we didn't have the data. So without the data, without treatment, we assume the growth that you saw in the first picture. And this is growing from 0 allele burden to 1. Then when we have the first measurement, we say, where does this fit in here? This is where we started the treatment of this patient here. So I could have put all these at time 0, which you would do in clinic, or we would say this all corresponds to the same disease, which is more or less progressed when we see them in clinic. So therefore, we wanted to show it like this. No. Yeah. Okay, let me go back. Right. So there was fitting one parameter, and the parameter has this biological interpretation of what happens at stem cell level, which is also the understanding of where the drug has an effect. One thing that was nice to discuss with medical doctors was a lot of people, clinicians don't use this allele burden measurements in general, right? So if you have a person coming in and you start treating them with some drug, you have some preferred levels here you want the thrombocytes and the leukocytes to be within. The drug is doing a good job. It's actually lowering the cells maybe too much. So maybe the clinician would say, not knowing this information, let me stop the treatment at this time point here. I'm in the middle of the range, everything is good. Then our model suggests a very quick relapse. If you waited here, and the reason it's going up here is because the dose is adjusted, then you would have a much slower relapse. And of course, the explanation is the coupling to the allele burden, which we have over here, that at this point, the stem cell effect of the drug is taking longer time to kind of be taking down the allele burden than the immediate effect here in the mature blood cells.
So why is the relapse so fast?
Here? Or
anywhere. I mean,
so
it must be at the level of the cell.
So the rebound here is fast because the allele burden is high. So you have an effect of the drug.
Oh,
Yeah. So the point of this one is that if you don't have the coupling to the allele burden, you could have very different clinical outcomes of stopping the treatment. So then Rasmus, our PhD student, also looked into like if you only had so all the stars here are data points. If you only use the first 3 data points for calibration, personal calibration of this curve, but you know the dose in the future. What would the trajectory be like in the model? Then you get the black curve here, which is we think good approximation to the actual data. And what would happen if you had stopped treatment at that point? That should be this one. What would have happened if you just stayed on the dose you were giving at this time and didn't increase it? Then you should have followed this curve here.
Sorry, that dosing pattern.
Yeah.
That's something that the doctor.
Yeah, that's the doctor. That's what the doctor did to the patient.
It's very weird. I mean, they have a rationale for it.
So they do. Well, they have some rules, and they sometimes follow them.
Are they feedback rules? If this is the verb and this is what I'm doing?
Yeah, but it's not only based on that. It's also as we saw before, the effect on the peripheral blood can be happening faster than on the allele burden. So you don't want the patient to go down here just because you then lower the allele burden, because it gives you other problems if you suddenly. Yeah, they have that in the trial, and when it's not in the trial, I think it's much more unclear to me how they make their decisions. Yeah, I must say. So this is a part of what I hope we can help them do, basically, with modeling. All right. So this kind of summing up some of this stuff, what you could do, and which is kind of we have a few patients without treatment, which could then say something about this curve you told us before, like the growth curve. And you can see some different untreated patients here, and what the growth could look like initially before you start treatment. You could then use this information and use the model to extrapolate back in time. I mean, I know we cannot, it's not fair to trust, what's happening out here, but we could do it, right? And what it suggests is that then if we want to say something about when the mutation happened from this, it depends on how many stem cells do you have, and there are different estimates. Now I think we are, what Kit said yesterday is we're closer to this estimate than like this estimate, but you can do different things. So the observed typical level is at 33%. So if we go back in time, this suggests that the mutation had happened something like 20 to 30 years before. Which, if it's true, gives a really long time to react, right? If we knew. So, Jordan, what should we do?
Yeah, so